Welcome, everybody. Thanks for coming. I wanted to remind everybody that if you can silence your cell phones, that'd be great. So my name is Anuj Gosalia, and I manage the SDK team at Oculus. Before joining Oculus, I spent a lot of time at Microsoft. I was leading the evolution of the Windows graphics architecture, including DirectX, for many years. It was great to be part of the evolution of graphics architecture from the earliest days of PC 3D graphics to where it is today. And I'm really lucky and fortunate to be part of Oculus and watch and participate in the early days of VR and see it evolve. So my goal for today's talk is to have an open discussion of how we are iterating the architecture of our SDK. I'll talk about how we got to our current architecture and what were the learnings we had so far, and then where we are headed moving forward. Hopefully, this will help you consider the impact it could have on your game engines. There will also be some future speculation, since we prefer to foster a discussion about things. There is a standard disclaimer. There's no guarantee on these future thoughts if they will actually be part of a shipping SDK. But it'll make for a good discussion, and it'll help you get an idea of the kind of things that we're looking into. Also, this is not a talk to help you learn of how to use the SDK. I have some great pointers at the end of my deck for that. But I think even people not familiar with the SDK will find this useful. So as you probably know, VR is very demanding. It's a really challenging and difficult problem space. It pushes the limits of the system in ways that few other problem domains do. The first reason is that we're trying to push a lot of pixels. We start by having a high resolution panel in our headset. The wide field of view of the headset means that still the pixels per arc second that you see is probably lower than similar resolutions on 2D displays. But we want to render at even higher resolution than the panel. This is because of lens distortion correction that we do. This distortion stretches pixels near the center and squishes them near the edges. To get great quality near the center, where the stretching happens, we need even more pixels in our rendered images. So we're looking to push almost 4 megapixels across both eyes. And even after this, we still really want high-quality anti-aliasing to be applied to the rendering. Add to this the fact that we're rendering in stereo, so the entire scene and rendering has to be done twice, and so there are overheads that come from that. Not only is rendering demanding, we now want to do all of this at really low latency. We want our motion to photon latency to be 20 milliseconds or even smaller if possible. So we push very high refresh rates, up to 90 frames per second. And we want to do this all in a virtually glitch-free manner. So we have a very demanding set of requirements to give good VR experience. So it's really important to internalize this, as we will have to work very hard to deliver on these kind of requirements and give a great VR experience. To explain how our SDK works today, I want to start with discussing what our goals were so far and what we have been focusing on. Given how important latency is to VR, we have heavily focused on latency over throughput. We have found that doing time warp as a way of adjusting orientation works really well and has been a big part of reducing orientation latency for us. We've also done a bunch of work to hide the VR headset from the operating system, which has been quite challenging. As we started down the path of VR, we have erred on the side of flexibility and experimentation. This was valuable as we were learning about what seems to work for VR and what doesn't quite work. So our earliest SDKs started with what we call app rendering. The main thing needed to render to our headset was to draw in stereo correctly and then apply a distortion pass to the rendered results. This distortion was needed such that the image looks correctly through our lenses. We provided the distortion code as reference, and it was up to the app to incorporate it into their rendering. The app did all the rendering to the render target that was then scanned out to our headset. This is a bit different from what came a little later in what we call SDK rendering, where the app calls our SDK APIs, which will do the distortion rendering on the app's behalf. In the app rendering approach, the app owned the entire rendering pipeline. It could experiment with different ways of doing distortion if it so wished. It could try fusing rendering with distortion and a bunch of things like that. So here's what that would look like. This is a simple diagram showing how the CPU and GPU work is done asynchronously to render a scene. In this case, the app is rendering comfortably at refresh rate. So these are time points of where vsyncs occur. And the app samples a pose at the start of its rendering. And this is the work that the app does on the CPU to traverse the engine and do all the work to make API calls, which eventually go to the graphics driver, and so on. The GPU actually picks up the rendering at some point later because graphics driver batch up a lot of these rendering commands and then submit them to the hardware when the batch is full. And so we provide the distortion code which the app appends at the end of its stereo rendering, and that gets queued and then executed by the GPU in this correct sequential order. So given that the app roughly samples a pose at the start of its scene traversal and rendering pass, and we start scanning out the frame at the next vsync, in this kind of scenario where the app is maintaining frame rate, you get roughly one refresh rate worth of latency from start to finish. And this is latency from sampling the pose to start of scan out. So I will use this type of diagram throughout my discussion to explain how we think about timing and latency. This is inspired by GPU View, which was a tool Microsoft built to understand and analyze GPU performance, which we find very useful in looking at VR apps and latency and so on. Last year, we talked about adding time warp, which is this idea to resample the orientation just before doing the distortion. We can basically use the incremental change in the head direction from the time we started the frame rendering to the time we are about to cue distortion. And then we warp the rendered image so that it looks like it would have been based on the updated orientation. We can actually do this warp and distortion in the same rendering pass, so it seems it's almost for free. This allows us to get a more up-to-date pose towards the end of rendering. At this time, around this time of introducing time warp, we also added the SDK rendering option, where the app creates a pair of iBuffers and renders to it, and then lets our SDK APIs do the actual distortion. And along with the distortion, we can now also do additional things like time warp. So this is what that looks like. Here, we sample the pose at the start of rendering, which is what is used to render the entire frame. But then, before queuing the distortion, we resample the pose, and we use that to adjust the image that is about to be rendered. So this gets queued up to the GPU, and then the GPU just does its distortion just in time before the vsync. So in this approach, we have broken up the latency to be what I would call time warp latency, which is shorter than the original start to end render latency. And we have now two types of latency to think about. The time warp works for orientation. So it handles the orientation latency, and it reduces that by readjusting for it with a later resample. But the positional latency is still the same as before. So we have now split latency into two parts here. and adjust it for orientation latency, which is quite important by doing time warp and resampling the pose. So we took this idea as far as we could. The goal is to try and do the time warp resample as late as possible. So our current SDK architecture attempts to try and push this as far as we can. So what we do is we basically wait till all the GPU rendering of your frame is finished before we schedule time warp, such that time warp doesn't get queued behind the app's rendering and it executes immediately. Also, if the app's rendering, like in this case, happens to finish really quickly, if the frame is relatively simple, then we wait further till a later point in the vsync before we schedule the time warp. And then after we schedule the time warp and it gets executed, we wait for the next vsync before we unblock the app, so that the app's sample pose is no sooner than the start of vsync. So if you're familiar with the SDK, after you finish rendering, you call OVR endframe, and that function takes all this time from the end of your rendering to the next vblank and does all the work to do time warp and timing and making sure that we can get a resampled pose as late as possible. So it reduces the time warp latency, but you still have the same render latency as before. So this is the architecture of our current SDK in terms of rendering. One of the key problems in VR is that existing operating systems are not designed for headset displays. Treating a headset as a 2D monitor leads to a bunch of unexpected things showing up and looking distorted in your headset. Also, the OS compositor usually gets in the way to having really low latency. On Windows, going into full screen exclusive mode helps, only when it works though. Also, it's being phased out. And so basically, it takes a lot of care and feeding to get to low latency, and it's not even always guaranteed. So this has been a tricky aspect of doing VR on existing operating systems. So we decided, let's try and hide the headset from the OS. We call this direct mode. This is in contrast to extended mode, where our headset shows up as part of the extended Windows desktop. To explain how this works, first let's take a look at the diagram on the left. This is a high-level overview of how Windows graphics stack works. You basically have the app that is making API calls to the D3 graphics APIs. D3, in turn, talks to the graphics driver in user mode to translate all these commands to hardware-specific stuff, sends it off to its kernel mode components, which then talks to the kernel mode graphics driver that schedules and submits all these rendering to the GPU. So that's like the very quick overview of how the Windows graphics stack works. What's interesting to see is how we achieve direct mode in this architecture. So we want to basically intercept the headset when the IHV graphics drivers detect it as being connected to the PC. So we introduced an Oculus graphics driver that sits in between the OS and the IHV graphics driver. And this basically intercepts our headset when it's being connected, and it tries and not avoid the OS from learning about it. And then we coordinate the display to this hidden headset using our SDK, and we also have to insert a shim between the app and the D3 runtime to coordinate how we do this. So this approach has some impact on how the app works, since the environment around the app has changed from what it would have typically been in a regular system. So with direct mode, we achieved our two goals. Now, only VR content shows up on the headset, which is really awesome. You don't see any of a window sticking up or your mouse getting lost on your headset and so on. Also, there is no extra latency anymore. There is no post-present latency. You call present, and it shows up in the headset at the very next vsync. However, there are some downsides. Our design is somewhat fragile to changes in the OS or drivers because it's sitting in between them and working around things in ways that they were not expecting. Also, it doesn't play well with other components doing similar stuff. And so things like hybrid graphics or wireless or USB display systems like DisplayLink, many of the performance tools like Pix and so on also insert shims between the app and the runtime, which conflict with direct mode. So there's a bunch of scenarios where this has some challenges. We also support a lot of different ways of doing VR. We have app rendering versus SDK rendering, as I just talked about. We support direct mode or extended mode. We support a range of graphics APIs, especially on Windows, where we support D3.9, D3.10, D3.11, and OpenGL, and a range of different operating systems. So there are a lot of valid supported combinations out there in this list. It gives a lot of developer flexibility, but it also gets hard sometimes to ensure that everything works well in all those cases. So now that I've described how we got to our current SDK, let's talk about where we're going. We have got a lot of feedback from you and other developers who use our SDK. And this has been very helpful for us and has been critical in guiding our future investments and focus. The first thing we want to do is improve stability. Doing VR is hard, and we are pushing beyond the limits of GPUs, drivers, and operating systems to achieve our goals. This has come at the cost of some stability. So improving this is a big part of our focus going forward. And it's also a big part of what motivates some of the changes that we are trying to work on. We really want to move to trying to do a few things really well instead of a whole bunch of features that have poor stability. The next area of improvement is efficiency. So far, we've been laser focused on reducing latency, even at the cost of throughput. However, one of the most common feedback that we get is that this is too difficult for many game programmers to work well within these constraints. So this is an important issue for us. Finally, we want to help out with resiliency. Getting to 5 nines worth of consistent frame rate is really hard. So how can we help make this better? These 3 areas have guided our next set of investments and changes in the SDK and software at Oculus. One of the things we expect to keep doing is that our API and the implementation behind the API is going to continue to keep changing as we improve things and tweak and make things better. These are still early days of VR, and we are not at version 12 yet in our VR APIs. So there's a bunch of fragility that comes from the dependencies that app takes on our runtime components. Today, we ship our libovr, which is where most of our SDK functionality sits, as a static lib that's shipped as part of the app's XE. However, we also have some runtime components that an end user downloads, and there's a bunch of private dependencies between our SDK, static lib, and our runtime components. By decoupling them and shipping them separately, we run into a bunch of mix and match issues whenever we ship a new runtime with existing apps. And that ends up becoming a problem for the developers who had functioning apps that suddenly stop working. So we're moving to a DLL model for our SDK, where we can ship the DLL with all the other tools in a way where they're all self-consistent. And then the app talks to our runtime components through our official SDK interface, which is an API contract that we can version and reason about. So by shipping it as a DLL, we have cleaner separation from the app, and it will help with some of the compatibility issues. We can also leverage side-by-side DLLs to ease API transitions as we keep improving and changing and adding functionality to our SDK. So the SDK, as I said, tries to minimize the time warp latency by trying to delay it as late as possible. And it potentially serializes the CPU and GPU to get this minimal latency. So to go back to the diagram that I showed before, you can see here while the CPU is working on preparing the scene, the GPU is kind of waiting for the command buffers to show up. It's not working on anything else. And then while the GPU is processing and rendering the scene, the CPU is waiting to issue time warp as late as possible, and so on. So there's a lot of gaps on the GPU and on the CPU in terms of processing. So, and as you see, we block your rendering all the way till vsync when you call OVR end frame. Also, the apps in the SDK are sharing apps device to do all the rendering. Our SDK does all the time warp rendering and all the scheduling and timing on your rendering device, on your rendering thread, using your HWind and swap chain and so on. To get all of these things functioning really well, we need to make sure we all follow a good set of rules, and if you get any of that wrong, it kind of breaks the experience. So we are moving to a new architecture at Oculus, which we call the Compositor architecture. This is a key step towards increased stability for us. The idea is that we want to isolate VR processing from the app. So we have a separate process that we do all our distortion and time warp rendering in. So it is a separate process, it's a separate thread. We use our own rendering device and swap chain, and we have our own HWind that we target all the rendering of that is supposed to go to the headset on. What this does is it moves a lot of the tricky code that has to be done just right to get the right monitor with the right orientation and the right HWind targeting our hidden display correct. All of that moves to our Compositor process. And the app is free to use its own device just to render the stereo eye buffers and use its HWind to display whatever it wants on a regular 2D monitor. For example, like our VR mirror view. So architecturally, this is what it looks like. Now the app's process, the app has an XC which calls into our SDK runtime DLL, and both of them leverage the standard D3 or other graphics API. And when the app is done rendering its iBuffers, it calls our APIs, which then marshals them across process to our Compositor, and then the Compositor does the time warp, the distortion, the other rendering features that we have added as part of our time warp distortion code. And also, this is the process that needs to deal with our hidden display in direct mode and so on. So as you can notice, we no longer have our Oculus UMD or our D3 shim in the app process. A lot of that is moved to the VR Compositor. So this makes the apps process free of any of our shims. This enables things like pics and so on to work for your app while you're in VR. From a timing perspective, this is what it looks like in the Compositor architecture. The app runs in its own process and thread. It samples a pose. It renders. It queues the two rendering eye commands. And when it's done, it calls into our Compositor. A Compositor, in its simplest incarnation, picks up these up-to-date. When it's finished rendering, it starts scheduling the time warp and distortion, which it queues up. In this case, we don't wait till rendering is finished because that added a bunch of fragility in terms of whether we'll make the time or not. So it does increase the latency because we just queue the time warp at this stage, and then it waits till the end of the frame and starts over. It does increase the time warp latency a little bit more than before, but we'll talk about some ideas that we are pursuing to help with that. But this kind of shows you the flow of rendering when we moved our time warp and distortion to another thread. So what are the implications of this kind of an architecture? The APIs for the Compositor are slightly different, and in my belief, a lot simpler than what we have today. One of the key changes we need to do as part of this is that the Compositor is the one that allocates a shared set of iBuffers that the app then uses as a render target. The reason the compositor needs to allocate the eye buffer is so that we can do the magic of shuttling them across process boundaries. It gives the compositor flexibility in the rendering style and API that it's using, and also how it synchronizes between queued app rendering and queued compositor rendering. The app could allocate its own eye buffers, but then we'll have to copy it into our shared eye buffer sets. While this may make it easier to port to our compositor architecture, it does waste precious bandwidth, so it's probably not the recommended approach. So anyway, the model is the eye just renders to our eye buffers and submits to the VR API. The other good side effect of this design is that our APIs are pretty identical across direct mode and extended mode. Speaking of extended mode, with the compositor architecture, we can enable a more reliable extended mode operation. It even allows us to tune and do some creative solutions to mitigate the impact of extended mode. And since the developer APIs are identical, the app doesn't need to be coded any differently whether we are running it in direct mode or in extended mode. The other idea that we started thinking about as part of trying to improve stability was to try and enlist graphics drivers' help in trying to hide the headset. So the architecture in this looks like we basically move the work that our drivers were trying to do into the actual graphics driver itself. So now the IHV graphics driver detects the fact that the monitor connected to one of its output is actually a VR headset and hides that from the OS. And then our compositor talks to the IHV drivers to deal with this hidden display and use that for VR rendering. With this design, our display driver is completely gone, and so we're no longer working around the IHV drivers. We still are, together with the IHVs, working around the OS, so that's still something to work on. The best case scenario would be if OSs support VR headsets natively, and that is something that we are hoping that the OS providers provide as VR gets more popular. The next big pain point that we have heard is that we use the GPU very inefficiently. And this is done to reduce latency. Typically, modern games on a regular 2D monitor queue one frame ahead, and this allows much better CPU-GPU parallelism. Engines are tweaked to minimize CPU and GPU sinks and stalls that come with it. In the ideal case, at 90 Hz, you should have full 11 milliseconds of CPU time and 11 milliseconds of GPU time before you glitch. However, when things are serialized to reduce latency, in the worst case, you almost have half the available time to do stuff on the CPU or GPU. The key downside, of course, of doing one frame queue ahead, as shown here, is that it hurts latency. So if you were to typical queue ahead operation of how normal 2D games work, is that while the GPU is processing frame 1, the CPU is queuing up frame 2, and then that gets picked up by the GPU at the next vsync and gets rendered. This approach allows great parallelism between CPU work and GPU work because they are staggered by a frame, but it increases the time warp and render latency. The thing to look at here is that we sample the pose over here on the CPU, and we encode it into our rendering commands of time warp. Typically, it's put into some constant buffer. But the GPU is picking it up right here much later and then processing with it. So we look at that, and we came up with this idea called late latching of the pose. The idea here is that what if we could, just before the GPU is about to process these constant buffers, fill them up with more up-to-date values of the head-mounted pose. So we have a sensor fusion thread that is doing sampling the orientation and all the sensors at a much higher rate than we do refresh. So on the Oculus Rift, our IMUs are being sampled at 1 kilohertz. So we have a lot more higher frequency way of understanding the pose. And sensor fusion happens also at a very high frequency. So with late latching of the pose, the concept is that we will treat these constants that are encoding the pose as volatile constants. And then we try and reread them, update them from the CPU such that we get a more up-to-date value before they're consumed by the GPU. So the design of late latching is that we define a constant buffer layout for what a set of pose parameters look like. And this constant buffer is tracked and persistently mapped onto the CPU. OpenGL already supports persistent mapped buffers. D311 doesn't quite, but we've been able to figure out a way to work around that. And moving forward, DX12 supports persistent mapped buffers on the CPU. So using this, the CPU keeps writing poses in a circular buffer within this constant buffer that we've marked. And then when the GPU is about to, before executing its rendering based on these volatile constant buffers, it basically needs to latch all the pose constants atomically. And it does that by copying these constants as part of latching the latest set of these values. And then we convert these latched pose values into final combined transform matrices in the vertex shader that is then used for the rendering. So late latching, the pose that is used for time warp, turns out to be relatively straightforward. And so we leverage the time warp distortion code to do queuing ahead of the time warp on the CPU. This helps us get back the orientation latency down to equal or even better than the current design. However, position latency increases if we queue ahead. So this is still a trade-off between VR latency and efficiency. But it's a step in the a positive direction. To make things really interesting, what if we were to late latch the render pose too? So here again, the app at the start of render typically samples the pose and then uses that to determine what to draw and queues up the entire frame of rendering of both eyes based on the cameras sampled by the pose. But again, since the rendering is queued, it doesn't actually read them till it starts actually processing it on the GPU, which is later. So what if we could resample the camera just before rendering of the actual frame in the GPU, and then again resample the time warp pose just before rendering the time warp distortion? So here we are late latching both the render pose and late latching the time warp pose. With this, we get perfect CPU-GPU parallelism and queue-ahead and no additional extra latency, because even render latency is shortened to almost the same as within a vsync. So this is perfect, right? We're done. We get awesome throughput and awesome latency. Yeah, but it's not as easy as this side. Designing game engines to render with an approximate pose is really hard. We need to adjust the shaders to key off these latched pose constants. We also need to deal with any view-dependent CPU work that happens in rendering. For example, many engines do very tight visibility culling. And if you change the view after the fact, if the camera changes position and orientation slightly, then you will see artifacts because you may be seeing things that were culled. And there may be other CPU view-dependent processing that happens in modern game engines that need to be accounted for. We're looking at trying to expand some of the viewing, frustum, and culling algorithms to have some extra room to account for small changes in the camera position and orientation. But overall, this is a pretty impactful change to modern game engines. However, if we can pull this off, this is a big win. We are currently actively working with Unity and Unreal to see if we can make this happen. If you are building your own game engine, it'd be really important for you to try and think about this and see if this can be made to work in your game engine and your graphics code, because this has a lot of potential to reduce latency and get back a lot of the efficiency. Part of trying to focus and getting great experience, moving forward, our team's focus is going to be a lot on SDK rendering. We have already a lot more features beyond just distortion that we do as part of the distortion time warp pass. With things like time warp, late latching, we talked about pixel luminance overdrive in past. There are things that we do in our time warp distortion pass that is a lot more involved. We coordinate across process boundaries to make it happen. We do all the things to track our hidden displays. So SDK rendering is the way to go to leverage all these investments. We're also dropping legacy API support so we can focus on modern graphics APIs. We're looking into not only, we will continue to support DX11 on OpenGL, and we are looking into supporting DX12 and other modern APIs moving forward. These new low-level APIs are a really good fit for VR because they reduce overhead and significantly reduce some of the CPU bottlenecks and even help with GPU efficiency. So if any of you, if this impacts you in a negative way, do come and talk to us. We would love to hear your concerns, if any. But this is definitely something that we'd like to try and do so that we can focus on more forward-looking APIs and feature set. So now I want to talk a little bit about our future directions. So like I said before, there's going to be a bunch of speculative stuff here, and there's no commitment that any of this will actually show up in our SDK. But it gives you a sense of what are the things we're thinking about and what are the directions and what are some of the trade-offs involved in trying to go down those paths. The first thing that we're looking at is asynchronous time warp. The concept here is to wake up at a particular time, typically late in the frame, and do the time warp with the latest set of iBuffers that have been completed. In this case, the app is running pretty well and it's running at full refresh. So we schedule our time warp at some point, and by the time we schedule our time warp, the app has finished rendering its most up-to-date frame. So we pick that up, and then we schedule the time warp to the GPU. And since in this case the app is running well at 90 Hertz, we have some pretty tight time warp latency and things look great. However, if the app's frame takes longer to render, then you glitch. So what happens here is that time warp, since it didn't get the completed frames from this frame, it picks up the old frame and time warps that and tries to schedule a time warp based on that. However, since the GPU was busy still drawing the previous frame, the time warp comes in too late and you glitch at this point. Now, if we could preempt the GPU, then in theory, we could always get a time warp to schedule it just in time and be able to get at least a transformed version of the old frame in time before the next vsync. So here, as soon as time warp is scheduled, we treat this as a high priority GPU rendering operation, and it pauses the app rendering and executes a time warp, which uses the last available frame and re-time warps it with the most up-to-date pose. So this frame gets drawn twice and reoriented to a more later pose. So instead of glitching, we at least draw the old frame with an up-to-date pose. This allows the time warp latency to stay consistently low. However, the render latency increases when we would have otherwise glitched. Now, GPU preemption is not exact. So it typically takes some amount of time from the time we say we want to preempt it to the time it actually does the preemption and starts executing the higher priority thing. So to deal with that, we have to schedule our asynchronous time warp a little bit sooner, or a lot sooner depending on what the GPU preemption granularity is. So this is an interesting trade-off. How we time and schedule a time warp has certain pros and cons. By moving it more earlier in the frame, we give ourselves some room to have enough time to deal with the preemption granularity and still ensure that our time warp shows up in time for the next vsync before, in cases that the app could have otherwise glitched. However, if we start too early, in some cases, when the app would have otherwise finished rendering and we could have done time warp with an up-to-date pose, we instead pick up, at this point we say like, what is the latest frame available? Since this is not complete, we go and use the previous frame and then time warp that. So we've managed to get very consistent time warped frames always showing up at frame rate and avoid some of the downsides of glitches. But in some cases, we actually increase the position latency or the render latency that we'd have. So there's an interesting set of trade-offs here. We know that position latency is bad, but then glitches or jitter that comes from it is even worse. So ATW is basically trading off position latency to reduce glitch. And it's important to get the timing right, depending on how well the OS and GPU can do the preemption. Today, GPU preemption support is pretty uneven. The good news is it's getting better with each generation of GPUs. Windows today supports GPU preemption. However, it doesn't really work so well in practice. Between the drivers and hardware and the OS issues, we've found that on existing version of Windows, preemption is not as well as we'd like it for doing ATW. We're looking forward to Windows 10 to see if things improve there. So ATW can help smooth over glitches. Could we use that to run on a steady state at a lower frame rate than the refresh rate? The thing to think about here, remember here, is that ATW only corrects for head motion. And even there, it only helps with the orientation aspect of your head motion. It doesn't help with position changes. And that's mostly because time warp is an orientation time warp. ATW does not help with the animation on the scene. So if you have animation, then if you're running at a lower frame rate, those things will impact what you see in the headset. And in some cases, it actually hurts. If it turns out that the animation direction is opposite to the direction of your head movement, you will have things go back and forth because ATW is pushing it in one direction and then animation happening at a lower frame rate is moving the objects in a different direction. Basically, running at a lower frame rate in a consistent, in steady state is effectively, we are trying to upsample temporally to get a higher frame rate. And this thing is something that has been well researched in the past, and there's a lot of attempts to doing that, and each of them has certain trade-offs and pros and cons. And we've not found this to work really well for a great VR experience yet. But we're trying. Earlier, I talked about how we want very high resolution for iBuffers to deal with the sampling pattern of our distortion mesh. So using one resolution for your iBuffers means that across the entire frame means that either we are oversampling in some areas or we're undersampling in some areas or probably both. For example, if you're rendering text, you really need to make sure that it's very high quality for readability. So in this case, you have text and you want to have really high sampling, so you want a very high resolution to make sure that your text and UI is readable. But what that means is that you're rendering a complex scene also at the same high resolution, which can often get very expensive and difficult. So we're considering this idea of layers and have layers of iBuffers. The idea here is that you could pull out the 2D UI into a separate pair of iBuffers from the world. So the 2D UI buffers can then be of relatively larger size, and they can be sampled well, and that will give you a high quality for text and other components. And these 2D rectangles can be placed arbitrarily in 3D space. And then the world scene can be rendered to another set of iBuffers, and that can be relatively a lower size because it's less important for that because there's no text or high contrast things in it. And that will enable us to hit glitch-free rendering on the world, which is complex and requires a lot more GPU and CPU horsepower. The 2D UI buffers tend to be relatively low complexity, so it's OK to draw that at a high resolution, and they often tend to get even updated less frequently. And then we can compose these two sets of iBuffers when we're doing time warp and distortion. In fact, we could potentially take this idea even further and extend this to multiple such layers. And here I've used the example of a game like Elite Dangerous. This is not real code. We have not actually done this. These are just ideas that we are looking into. But the point is that we could do that for n such buffers for various UI components. The other thing that we've been looking at for some time is positional time warp. So the idea here is not just to do a warp to cover up for orientation, but also attempt to try and adjust for translation. And so we've looked at various reprojection techniques to do this, but they do have perceptual artifacts in VR. So there's a whole bunch of stuff we are looking at and approaches, but we're not at the point where we feel that this can be made to work really well. But we're ongoing some research on this, and so we'll let you know if we find something that works well for various cases. VR is still pretty new, so there's a lot of things that we are still experimenting with. This is not even a vaguely complete list of things that we're looking at, but I wanted to talk about some of the kind of directions that I think will be interesting as we move forward. So rendering peripheral areas of our iBuffers, where the sampling is less and we are undersampling the rendered iBuffers, we're looking at various ways to do multi-projection such that we could render the peripheral areas at slightly lower resolution and get back some perf. So there's some various ideas of different multi-projection that we could be using. We're going to continue taking certain various stabs at temporal upsampling to see if there are ideas and algorithms that work in certain cases that help. We're also looking into expanding the notion of layers to more than just 2D UI and see what else we could do there. One of the interesting areas that I think will be very interesting to pursue is this notion of multi-rate decoupled rendering engines. Could we look at ways where certain parts of the engine processing is happening at a rate that is lower than the full refresh rate? I was already talking at this GDC to some engine developers where people are pursuing engine architectures where, say, the shading rate is completely decoupled from the rasterization rate. These kind of techniques might prove really valuable for VR, where we can have the thing that is required to draw the scene run at refresh rate, but some of the heavier processing like gameplay, AI, physics, global illumination, maybe entire shading runs at a little bit lower refresh rate, and see how that looks like. So we have a long list of ideas from interesting to wildly crazy that we keep pursuing, and I hope to discuss these things regularly with you guys as we move forward. So with that, there's some pointers to further information. There are some older presentations that we've done that will help you with how the SDK works and so on. We've come up with a couple of blog posts recently that go into more details on some of the topics I've talked about. And in general, our Oculus blog is a great resource for looking at things that we're up to, and we from time to time post some good technical posts that you may find interesting. So thank you again for coming, and we have time for some questions. There's a microphone in the center if you want, and that way everybody can hear your question. But that's where we are right now. And with this, I hope you guys have an idea of what are some of the directions we're trying to move towards in the Oculus SDK. All right, thank you.